So we have seen different ways by which we can check the stability of a control system. But one such way in which we can check the stability of a control system is by plotting a particular plot referred to as the Nyquist plot. So how do you check the stability of a control system by plotting the Nyquist plot? Well, my name is Rishi Remju, and welcome to the Backbench Engineering Community, where I'm making engineering easy for you. So let us ask ourselves that obvious question. How do you check the stability of a control system by plotting the Nyquist plot? Well, let's find out. So, in order to understand how we find the stability of a particular control system using the Nyquist plot, let us consider this particular example. Draw the Nyquist plot for the open loop transfer function g of s is equal to 1 divided by s squared into 1 plus s into 1 plus 2s and determine its stability. So here, the Nyquist plot is mainly based on something referred to as the Nyquist contour. It is based on a Nyquist contour. So what is a Nyquist contour? So for that, let us first consider the basic S-plane that we have seen. So in the case of an S-plane, here we have sigma and here we have j omega. So a Nyquist contour would look somewhat like this. It is somewhat like this. This is what you refer to as a Nyquist contour. So here, the interesting part about an S-plane is that here when we consider the anti-clockwise direction, here we would have 0 degrees, here we would have 90 degrees, here we would have 180 degrees, here we would have 270 degrees, and here we would have 360 degrees. But when we consider the clockwise direction, when we go like this, here we would have minus 90 degrees, here we would have minus 180 degrees, here we would have minus 270 degrees, and here we would have minus 360 degrees. So here, this is basically what you refer to as a Nyquist contour, this particular portion. So here, first let us consider this particular part like this. Let us consider this as part number 1. So here, when we consider part number 1, what we observe is that here it moves from here to over here like this. That is along the positive j omega axis. Like this, from here to 90 degrees. So here, in this particular portion number 1, let us take s is equal to j omega. So here, in this particular portion, we have to put s is equal to j omega. And now, next comes the interesting part. Next, here then what we observe is that it now moves along here like this. So this is the Nyquist contour. So this portion number 2, let us assume this as portion number 2. So in portion number 2, we have an infinite radius contour. So here in portion number 2, we have an infinite radius contour. So here, let us assume that this particular contour is represented as r into e raised to j theta. So here it is of infinite radius, so which implies that this particular radius tends to infinite. And here the value of theta, when we observe carefully, we can observe that it varies from plus 90 degrees to minus 90 degrees. So therefore here it can be represented as s is equal to limit r tends to infinite r into e raised to j theta, where the value of theta varies from 90 degrees to minus 90 degrees. Now, let us now substitute this particular thing over here in this particular equation. Substituting this over here, we would now get the value of the open loop transfer function as g of s is equal to 1 divided by, here we have s squared, but s is limit r tends to infinite, r e raised to j theta. So here, let us take limit r tends to infinite as common outside. So here, s squared, that is this particular term, the whole square. So this becomes r squared into e raised to 2j theta multiplied by 1 plus s, which is 1 plus r into e raised to j theta, and 1 plus 2s. So this becomes 1 plus 2 into r e raised to j theta. So now here, let us now take this r e raised to j theta outside as common and this 2 r e raised to j theta outside over here. So taking these two terms outside over here, we would now get this is equal to g of s is equal to limit r tends to infinite 1 divided by 2 into r raised to 4 e raised to 4 j theta into 1 plus 1 divided by r e raised to j theta into 1 plus 1 divided by 2 r e raised to j theta. So here we have r tends to infinite. So here we have 1 by infinite and 1 by infinite, but 1 divided by infinite is 0. So here we have 1 plus 0 into 1 plus 0. So this becomes 1 and this becomes 1. So this ultimately becomes limit r tends to infinite. Here we have 1 divided by 2 r raised to 4. So 1 divided by 2 r raised to 4 multiplied by e raised to minus 4 j theta. This term I am taking it to the numerator. So here this is the magnitude and this is the phase. So here the value of the magnitude, when we put r is equal to infinite over here, 1 by infinite is equal to 0. So here the value of the magnitude is equal to 0. And now here, considering the phase, here we have e raised to minus 4 j theta. So here the value of theta varies from 90 degrees to minus 90 degrees. But here it is minus 4 theta. So the value of the phase varies from minus 4 into 90 to minus 4 into minus 90 degrees. So here minus 4 into 90 is given as minus 360 degrees. And here minus 4 into minus 90 is given as plus 360 degrees. So that is what we get over here in this particular infinite loop contour. And now after this, it now moves along here like this. Let us consider this as portion number 3. So in portion number 3, we can put the value of s as s is equal to minus j omega, because it is moving along here from minus 90 degrees to 0. And finally, in portion number 4, we see this small portion over here like this. This very small portion over here. So here, in this particular portion, this moves from minus 90 degrees to plus 90 degrees. So here it moves from minus 90 degrees to plus 90 degrees. So here, considering that, when we consider here, the value of radius is very small. So here, the value of radius tends to 0. That is, it is tending to become equal to 0. So let us assume that here s can be represented as s is equal to limit r tends to 0 r into e raised to j theta. Because the value of the radius is tending to be 0, tending to be very small. So let us take limit r tends to 0, r into e raised to j theta. Now let us now substitute this particular value in this particular equation over here. On substituting this over here, we would now get the value of the open loop transfer function as g of s is equal to limit small r tends to 0, 1 divided by here s squared, that is r squared into e raised to 2 j theta into 1 plus r e raised to j theta into 1 plus r 2r e raised to j theta. But here, when r tends to 0, this also tends to 0 and this tends to 0. So this term becomes 1. So here, similar to this, we get over here limit small r tends to 0. The magnitude is 1 divided by r squared and the phase becomes e raised to minus 2 j theta. So therefore, this is the magnitude value and this is the phase value. So here, when the value of r tends to 0, the value of 1 by 0 would be infinite. So therefore, the magnitude value becomes infinite. And now here, the phase is minus 2 theta. But here the phase varies from minus 90 degrees to plus 90 degrees. So here, we would get the phase as minus 2 into minus 90 degrees to minus 2 into plus 90 degrees. So here minus 2 into minus 90 degrees is 180 degrees, and here minus 2 into plus 90 degrees would become minus 180 degrees. So here the value of phase varies from 180 degrees to minus 180 degrees. So it is now based on this particular Nyquist contour and all these datas, all these 4 datas that we have obtained here. That is when here this particular portion number 1, this particular portion number 2, which is an infinite contour, and then in this particular portion number 3, and this tiny little portion number 4. So it is based on this we are going to plot the Nyquist plot over here. So in order to plot the Nyquist plot, we have to first obtain the polar plot, and it is from this particular polar plot we obtain the Nyquist plot. So here from this, let us now obtain the polar plot from this. So now let us now plot the polar plot over here. So in order to plot the polar plot, what we have to do is that we have to replace the value of s as s is equal to j omega. So step number 1, let us assume that the value of s is equal to j omega, then we would get the value of g of j omega as g of j omega is equal to, here wherever we have s, we have to substitute the value as j omega. So this would now become 1 divided by j omega squared into 1 plus j omega into 1 plus 2 j omega. So now step number 2, we have to write it in the standard form. So in the standard form, we would get the magnitude value, that is the magnitude of g of j omega and the value of the phase of g of j omega. So the magnitude of g of j omega is given as g of j omega magnitude is equal to 1 divided by, here we have j omega squared, so the magnitude of that would be just omega squared. Here we have 1 plus j omega, that is root of 1 plus omega squared. That is because the magnitude of a plus jb is equal to root of a squared plus b squared. So here the root of the real part squared plus the imaginary part squared. So root of 1 plus omega squared. Similarly here also we would have root of 1 plus 4 omega squared. That is the magnitude of g of j omega. Now the phase of g of j omega is given as this is equal to, here we have j omega squared, so that would become minus 180 degrees. That is in the denominator, that is why we have minus 180 degrees. Minus, here we have 1 plus j omega, so that becomes tan inverse imaginary part by real part, that is tan inverse omega by 1, so that becomes tan inverse omega, minus here also we have tan inverse imaginary part by real part, so imaginary part is 2 omega, so this becomes tan inverse 2 omega. So that is the phase, that is minus 180 minus tan inverse omega minus tan inverse 2 omega. So now after this, step number 3, we have to find the value of the magnitude and the phase at omega is equal to 0 and omega is equal to infinite. So at omega is equal to 0, we get the magnitude of g of j omega is equal to, substituting the value 0 over here in this particular equation, we would get this as 1 divided by 0, which is equal to infinite, because here we have omega which becomes 0 and 1 by 0 is equal to infinite. So here the magnitude becomes infinite. But the phase of g of j omega becomes, here substituting the value as omega is equal to 0 in this particular equation, we have minus 180 minus tan inverse 0 is 0. And here tan inverse 2 into 0, which is equal to tan inverse 0, that is also 0. So here this becomes minus 180 minus 0 minus 0, which is equal to minus 180 degrees. So next let us take the point at omega is equal to infinite. So at omega is equal to infinite, substituting the value over here, we have 1 divided by infinite into infinite into infinite. So 1 divided by infinite is equal to 0. Therefore the magnitude of g of j omega becomes 0. And now substituting the value of omega is equal to infinite over here, we would get minus 180 degree minus tan inverse infinite is 90 degrees. So, and tan inverse infinite becomes 90 degrees. So this becomes minus 180 minus 90 minus 90, which is equal to minus 360 degrees. So therefore the phase of g of j omega is equal to minus 360 degrees. degrees. So here we have found out the value of the magnitude and the phase when the value of omega is equal to 0 and when the magnitude of omega is equal to infinite. So the next step that we have to do is that we have to now separate the real part and the imaginary part from this particular equation. That is, from this particular equation, g of j omega is equal to 1 divided by j omega squared into 1 plus j omega and 1 plus 2 j omega. We have to now separate it into two parts, where one part consists of the real part and the other part consists of the imaginary part. So here we have g of j omega is given as 1 divided by j omega squared into 1 plus j omega into 1 plus 2 j omega. So here, in order to convert this into two parts, which is the real part and the imaginary part, we have to multiply this with the complex conjugate of the denominator. So if we have to multiply and divide this by the complex conjugate of the denominator, so that becomes here, this is 1 plus j omega and 1 plus 2 j omega. So the complex conjugate is 1 minus j omega and 1 minus 2 j omega. Let us now take 1 minus j omega and 1 minus 2 j omega. We have to divide it as well. 1 minus j omega, 1 minus 2 j omega. So now on multiplying, dividing it with the complex conjugate, here we would get this equal to 2 omega squared minus 1 divided by omega squared into 1 plus omega squared into 1 plus 4 omega squared plus j3 divided by omega into 1 plus omega squared into 1 plus 4 omega squared. So that is what we get. So here we have the real part and here we have the imaginary part. So now the reason why we have split these into two parts, that is the real part and the imaginary part, is because we need to find the intersection of this particular plot with the real axis and the imaginary axis. So that let us now find the intersection of this particular plot with the real axis. So intersection with. So first, with the real axis, so in order to find the intersection with the real axis, what we do is that we take the imaginary part and equate it to 0. So with the real axis, the intersection is obtained by equating this particular part equal to 0. So when we equate this particular part equal to 0, what we observe is that this particular denominator becomes 0 and j3 becomes equal to 0, which means that there is no intersection with the real axis. So therefore, we have no intersection. But now, when we find the intersection with the imaginary axis, what we do is that we take the real part and equate it to 0. So, when we take the real part and equate it to 0, what we obtain is that we get 2 omega squared minus 1 is equal to 0, or omega squared is equal to 1 by 2, which implies that omega is equal to 1 by root 2. So now substituting the value of omega is equal to 1 by root 2 for the magnitude and the phase, we would get the magnitude of g of j omega is equal to, when omega is equal to 1 by root 2, this particular value becomes equal to 0.94, and the phase of g of j omega becomes equal to, on substituting the value of omega is equal to 1 by root 2 over here in this particular equation, we would now get the phase of g of j omega is equal to minus 270 degrees. So now we have obtained the required things that we need in order to plot the Nyquist plot. So first let us plot this particular plot over here. Let us take a particular plot over here like this. So here we have sigma and here we have j omega. So now here in this particular step, what we observe is that when the value of omega is equal to 0, the magnitude of g of j omega is equal to infinite and the phase is minus 180 degrees. So here from infinite over here we have a plot coming like this with a phase of minus 180 degrees. And here the value of omega is equal to 0. And now when the value of omega is equal to infinite, the value of g of j omega is equal to 0. And it has a phase of minus 360 degrees. So it would be somewhat like this. It would come like this over here. So here this is when omega is equal to infinite. And here we have obtained the intersection, the point of intersection as 0.94 with a phase of minus 270 degrees. So here taking minus 270, here we have minus 90, minus 180, minus 270 degrees. So at a phase of minus 270 degrees, the intersection is at 0.94. So therefore the plot would look somewhat like this. It would go like this, like this. It would intersect at 0.94. It would go like this, and it would end over here like this. So now, from portion number 3 of the Nyquist contour, we have to now plot the inverse polar plot of this. So here, if this is like this, then the inverse polar plot would look somewhat like this over here. It would go like this, like this, like this, like this. So this is the inverse polar plot over here. And now, from portion 2 of the Nyquist contour, we have seen that the value of the phase varies from minus 360 degrees to plus 360 degrees with a magnitude of 0. So this happens as 2 circles in the anti-clockwise direction like this. So this is 1 circle and this is 2 circles. So these are very small circles. I'm just drawing it a bit more bigger so that you can understand how these circles are drawn. Because the value of the magnitude of these circles are tending to become 0, very small. So there will be 2 concentric circles like this, because it varies from a phase of minus 360 degrees to plus 360 degrees. And now, from the part 4 of the Nyquist contour, we have a plot varying from plus 180 degrees to minus 180 degrees. So that is, it has one particular circle in the clockwise direction, and here we have the magnitude is equal to infinite. So here when we plot this, it would look somewhat like this. It would originate from here, and here it would complete one particular circle like this, and it would terminate over here in the clockwise direction like this. So this is the required Nyquist plot that we now require. So now the next obvious question that you would be asking is, how do I determine the stability from this particular Nyquist plot? How do I determine it? So to find the stability from the Nyquist plot, we take the equation as, here the stability is obtained by n is equal to P minus Z, where n is the encirclement, P is the number of poles that are present in the right half plane for an open loop system, and Z is the number of poles in the right half plane for a closed loop control system. So here in this particular plot, what we observe is that here we have one encirclement like this, and here have another encirclement like this, but both of these encirclements are in the clockwise direction. So therefore the value of n is taken as n is equal to minus 2, since we have two encirclements in the clockwise direction. And now here, when we consider this particular open loop transfer function over here, what we observe is that when we equate the denominator equal to 0, we get the value of the poles. So here, first when we equate s squared is equal to 0, we get s is equal to 0. When we equate 1 plus s is equal to 0, we get s is equal to minus 1. When we equate 1 plus 2s is equal to 0, we get s is equal to minus 1 by 2. So from this, what we observe is that there are no poles lying in the right half plane, and that is in the right half side of the S plane. So therefore here we get the value of P is equal to 0. So therefore substituting these two in this particular equation, we would get minus 2 is equal to 0 minus Z, which implies that Z is equal to 2, which implies that there are two poles lying on the right half plane in the case of a closed loop control system, which states that the closed loop control system is not stable. So this is simply how you determine the stability of a particular control system using the Nyquist plot. As simple as that, guys. There's nothing more to it. As simple as that. So I hope you guys now have a clear understanding of how you can find the stability of a control system using the Nyquist plot. And if you guys found this video informative, please do hit the like button and join this community by hitting that subscribe button. We'll be discussing about the further topics in the upcoming videos. So stay tuned, stay subscribed. Until next time, I'll see you guys in the next video. Thank you.